we're going to get started into chapter 3. It's more on kinematics. That's good news and bad news. I think the real good news is you probably at this point are still kind of struggling along with those equations and those kinematics that we just did in chapter 2. Chapter 3, though, is a lot like chapter 2. So this will help, I think, expand your knowledge as you try to finish up chapter 2 and then as we get into chapter 3. And you'll see more about that when I explain. But I want to take just a moment, especially for you guys, mostly online people, not so much you in-person people, and just jump over to the Canvas page for just a second. So I started my Canvas page. Yours will probably look a lot different than this because I got a lot of different classes, but this is your class. And so I'm assuming all of you, both in person and online, have been able to find your Canvas. I've got a bunch of questions, but none of them had been about, I can't get on Canvas. So I would assume that's working well. When you go to Canvas, it'll look something like this. I set the home page really to be your assignments. Yours will probably look a little different. In fact, I'll just click here on Student View. And so this will give a better representation of what it would look like for you guys. And again, this is especially for you guys online because we've had some little technical challenges for you guys online. Not you guys in person. You guys in person have already done 2 labs and turned them in and actually have been graded and all that's good. But for you guys in person, on the first day, the computer system was down. Last night, we finally got a chance to record the first and second lab. But then we had some computer issues. So far, and I apologize for this, you have not gotten the introductory lab. And you haven't got the second one, which is the acceleration due to gravity. We processed it last night. In fact, Ron, I meant to ask you when you came in, it's all good and going? All right. So later on today, I'm going to go ahead and get those out to you. You'll actually get those before we have a chance to render this video. But I wanted to say, because a lot of you are start asking and getting worried, that, hey, we don't have the labs yet. I just want you to know, I understand that. The problem is on our end, and you won't be penalized for that. So know that even though it says it is due in the first 3 labs that we're doing this week, even though it says they're due this Sunday night, I just wanted to begin by saying, I know there's a problem. Hopefully you can still do it by Sunday night. But if anything's late on this first week, no worries, no penalties. I totally get that. And I'll send an email saying the same thing here. But like I said, I just wanted to start that. In fact, it's even more complicated because if you actually click on the assignment, there's nothing here to tell you what to do. And I know that's why a lot of you online are clicking on it going, well, it's due Sunday night. I should get started on it. What do I do? And there's nothing there. I should probably take some time and write it, but what I was waiting for is for the video, because what I'm going to do is give a few instructions and post the video right there to tell you how to do the introductory lab, which, as you will soon see, and I probably shouldn't say too much about it, but the introductory lab teaches you guys from home how to log in with your computer and how to use our virtual desktop and to use one of our programs called graphical analysis. And of course, you guys in person know that. That's what you guys already did, was learn about graphical analysis. So anyways, more of that is to come, and I will start working diligently on that tonight and Thursday, and so you'll have Thursday, Friday, Saturday, Sunday to do them, and you'll even have next week if you want it, because the problem's on my end. All right. So with that said, let me leave then that and say, okay, let's begin class today here. And so I'm going to come over here and say, moving on to chapter 3, which is more kinematics. I will start by, let me change that for the glare and maybe for the cold, but I don't know if it's cold today, but it might be. Let's look at chapter 3, and I'm just going to put up here, this is two-dimensional kinematics. And so most of you are still probably working in chapter 2, trying to do those homework problems. And of course we did them at the end of the lecture. I did 3 examples for you, and I did 2 other really hard examples last night. In fact, I'll ask you guys in person, anybody see that video, or at least no, I sent it. How about that? Okay, and then there's anyways, one problem had solving a quadratic in it, and so I wanted you guys to see that, and I was bummed I didn't get a chance to show you that in class. So I want to encourage everybody, both at home and here, to go ahead and watch that, because it just showed some more math. And the other one was a problem that is very interesting and challenging and a hard one, and it's from the university physics book, but it's one that had an acceleration. In fact, I remember it was Usain Bolt running, and it had a constant acceleration for part of the race, and then a different acceleration, which was 0. They just ran at a constant speed for the other part of the race. And I just wanted to emphasize, how do you do something like that? Because the whole race is not a constant acceleration, but the pieces are. And so you can use those equations for constant acceleration if you're careful with them. You just can't use them for the whole race. You got to use them in 2 pieces. And that's what I was trying to illustrate. So I want to encourage you to watch those, because, again, those 5 equations I gave you are really nice in the sense that they came from the calculus we worked out, and then you don't have to work out the calculus. You just have to look at those 5 kinematic equations that are valid for constant acceleration and use them. And that's what I was trying to emphasize. And we'll continue to emphasize today here. But what I was kind of leading at here is we've done one-dimensional motion, and you guys are learning about one-dimensional motion, and so we're going to expand on that and say, well, what would happen with something like this? Let me just grab an object that hopefully won't break. How about this steel ball? And if I were just to go this way so I don't lose it here, but if I were just to kind of throw it, you will hopefully see that as it moves, it's moving both along the x-axis and the y-axis. At first it went up a little bit, and then it went down. Let's see if I can find it now. I'll need that later on. And that's what I'm talking about here. Here is the good news that I want to show you at the beginning. How do we do a problem that is 2-dimensional motion as compared to 1-dimensional motion? And so that's the step up. And so that is the difference between last chapter and this chapter. This is our learning of physics. Each day you'll, of course, discover, we go to the next chapter and we learn something new, something more advanced, something more complicated, something, I would say, more closely related to the real world. Because one-dimensional motion doesn't often match the real world, except for maybe Usain Bolt running the 100-meter dash. That's one-dimensional. But tossing a ball is 2-dimensional. And then, of course, we could have something more complicated, like the movement of a roller coaster, and it's 3-dimensional. It moves x and y and z. But getting here with 2 dimensions, I'm going to say this to start. How do we do calculations, and then by calculations I would say physics and predictions of where the object's going to be in 2 dimensions? And it's actually surprisingly simple. We were going to do one-dimensional motion twice. This is why before we started the lecture with the camera, I was telling you in-person people that today's chapter will really help you out with yesterday's chapter. Because what you're going to see me do is a bunch more examples, and I will do 2-dimensional examples, but the way I will do them is I will do x separate from y. And so I will be just doing 1 dimension twice. So it's really important you learn how to do 1 dimension first. Then it makes this chapter fairly straightforward, because we'll just do 1 dimension twice. I like to put it this way. That is, ... You want to think in your mind and solve with your equations the x and y motion separately, or I'll put here independently. Now, the best place then to start with this is to demonstrate to everybody that this is the way nature behaves. Obviously, we don't want to think and solve our problems independently if nature doesn't behave independently. So, we have some very simple experiments to kind of show you. And this first one will hopefully illustrate the independence of something going across the room where the X motion and the Y motion can be analyzed, can be thought about, can be calculated separately. See this little contraption right here? It's pretty simple. It's got a little handle. It's got a little spring. I can pull it back and I can lock it in a notch. Or I can lock it in a second notch. And when I lift it up, the spring just pushes the shaft that way. So if I just put it back on the first notch, and I take this one sphere, which has a borehole in it, and I put it right on the end, if I lift it up, what will happen is this shaft will scoot over, and gravity will pull the ball straight down. I would call that one-dimensional motion. So this ball here is to illustrate one-dimensional motion in a vertical drop. Okay. But at the same time, I could put a second ball right at the edge. So when I release it, this shaft is going to push that ball horizontally. Of course, when it does that, it's off of the surface, and so it begins to fall also. And so this one has a two-dimensional motion with it. It's got an initial kick in the X direction, and then as it is moving along, gravity is pulling it down in a vertical direction. But here's what I want you to watch. I want you to watch that even though this ball is moving over in the X direction, watch its vertical motion. That'll work. The king chair, that's what I like to call that, is in the way. All right, so let's say it again. Watch this more vertical motion, because I want to convince you that the vertical motion of this one is exactly the same as the vertical motion of this one, even though this one has horizontal motion and this one does not. That's my way of saying nature treats them separate. Nature's not going to care that this one has a horizontal motion. It's still going to pull it down at the same rate and the same distance and the same time that this one goes down. And so watch if these don't hit the ground exactly at the same time. It'll look something like this. It'll go straight down on this one, and this one will go over, but they'll always be at the same height. They'll hit the ground at the same time. They'll even bounce a little bit at the same rate. And everything about the vertical motion will be the same, even though this one has horizontal motion. All right, so let's give our first experiment a try. 1, 2, 3, go. And so didn't they hit at the same time? Weren't they at the same vertical height? I mean, let's watch it a second time. This time, let me go to the second notch, because I would say the second notch makes this ball get kicked even harder towards, well, your right, my left, okay? But the vertical motion will still be the same. And so this is my little experiment to try to prove to you the reason we're going to think and the reason we're going to solve and we're going to, excuse me, do all of our motion where the X and Y are separate is because that's how nature behaves. And so once you understand how nature behaves, this makes totally sense why we're just going to make two columns and say one column, let's calculate where it is on the X-axis, and another column that says, okay, let's calculate where it is on the Y-axis. All right, well, let's take a look at this one. And I want to emphasize, even though this has a bigger X motion, the Y motions are still the same. All right, 1, 2, 3, release. And so didn't they hit at the same time? And so that's my very, I'll call it low-tech way of trying to show you how the physical world behaves. And so knowing how the physical world behaves, that's why we'll treat our math that way, because that's what we're trying to do. We're trying to use some math to describe the physical world. If the physical world didn't work that way, well, then there's no point in doing our math that way.
So if it was like, if they had different heights starting, it would have different y motion?
I'll say yes and no to that, because it depends how you're thinking. See, if I were to start them at different vertical heights here, and I let them go, in a fraction of a second, they would each fall the same distance down, okay? But they wouldn't ever hit the ground at the same time. So part of me, and this is what I think you're thinking, is I would say they have the same motion, because they would do something like this. This one would hit, and then this one would gain speed. So this one would actually hit with a greater speed than this one, because this one had a more time to fall. But, and so that's what I'm getting at. Depends how you're thinking about that. If you're saying they have the same vertical speed when they hit, I'd say no. So then they're not the same. But if you're saying in your mind, and it sounds like you are, you're saying, well, they have the same motion, just the motion of this one and the motion of this one are shifted in space, then I'd say, yeah, they're the same. Yeah. So in other words, it wouldn't matter if I dropped it here versus here. They're each going to have that acceleration of 9.8. Just this one has more time of acceleration, so ultimately hits the ground at a greater speed than that one. Okay. Now let me show you a little higher tech one. Still nothing really that fancy, but it illustrates it, and it's kind of fun to see. This has got some electronics in it, so I'm going to turn it on. Maybe you can even see a little flashing light here. But here's the object I'm going to shoot, if you will. There's a little cannon. Maybe I'll try to stand over to the side so you guys on the camera can see it better. But it's a little spring-loaded cannon. So I'm going to push it down and load the cannon. And the electronics releases the spring with a little infrared beam that is between two notches right here. And so at least for you guys in person, like we did in yesterday's lab and the second lab, and you guys online, you'll see the infrared device when we do the second lab. But if I just put this card right between there and break the beam, you'll see it shoots the cannonball up. All right, I'll show you again. So put it here and launch the cannon. Now, if I got the cannon adjusted correctly, it shoots straight up and, of course, then comes straight down. So I would say this is one-dimensional motion. I would say this just gives it an initial vertical speed. Of course, gravity slows it down. It comes to zero speed, and then it falls back down. Fair enough? One-dimensional? Yeah.
When it would reach, like, its peak height,
yeah,
does that mean acceleration would be 0 to?
Ooh, great question. And for you guys online, she asked, when it gets to the top, is it acceleration 0? This will give me a chance to say, careful. This was my warning of last chapter. It's easy to confuse speed and acceleration. They're not the same thing. So, at the very top, what has happened is its motion, its velocity is 0. That's what's 0. But its motion is changing, right? It's going from up to down. And the change is the acceleration. So when it gets to the top, what's 0 is its speed, not its acceleration. It is changing. Now, maybe that's better described taking you back to your calculus class. If I had an x and y axis, and I had a function that looked like this, you might recognize it maybe as a sine curve right here. I've got two questions for you. One, what is the value of the function right there? Two, what is the rate of change or the slope right there?
Are those the inflection? Are those the inflection points? Or it's like
I think that is an inflection point, but let me say that's not quite what I'm getting at. So, yes, but, how's that? What I'm trying to say is, isn't this a value of 0? That's what the y-axis means. But the slope, the change, is not 0. So the value can be 0, but the changing of it is not necessarily 0. And that's the same thing for a ball going up. A ball goes up, slows down, slows down, slows down, slows down, stops. So its speed is 0, and then comes back down. So it's going from positive to negative. And it has a 0 right at that moment. And that's what this function is. This function is going from positive to negative. And it's 0 at that moment. But the slope is not 0. So I will say, to answer your question, the acceleration at the top is still 9.8, negative 9.8. The acceleration is always negative 9.8. If the ball's going up, what's the acceleration? Negative 9.8. If the ball is at the top, what's the acceleration? Negative 9.8. If the ball's coming down, what's the acceleration? Negative 9.8. And we go back to a comment I made yesterday's lecture, is it's so easy to go, well, but professor, it's going up. But professor, it came to a stop. But professor, it's going down. But professor, it's Tuesday. But professor, it's green. So what? I said the acceleration is negative 9.8. Always. Okay. And so it doesn't feel like it at first, but it's really that simple. Physics is about knowing how a few powerful, fundamental ideas explain a universal phenomenon. Questions?
Oh, wait, you said when it's moving up, it's negative 9.8, or it's moving positive, right?
No, it's pulling down still, right? When it's going up, it's pulling it down, and that means right? So let me round the 9.8 to 10 for a second. If I were to throw it up at 20, I would say then the acceleration is a negative 10, and so that means it changes its speed by negative 10. So if I throw it with 20, a second later it is now 10. A second after that, it is now 0. A second after that, it is now negative 10. A second after that, it's negative 20. And so it's always changing by negative 10. Even on the way up, it's changing by negative. And of course, if you have it going up, so you have positive numbers and you take away, it's getting smaller. But on the reverse, when it's going down and you have negative numbers and you're subtracting, they get bigger negative, if you'll let me say that. It'll get more negative, right? And so going down, it goes faster and faster. So I'll say it again. Don't make it complicated. It's not one value up and one value down, or one sign up and one sign down. It's always negative 9.8. At the top, on the way up, on the way down, even if it's green, blue, or orange. Okay, well, back to what I wanted to show you then, is what would then happen if I also gave it a horizontal motion when the cannon fires. And so this little post right here will actually break the infrared beam when it goes across, and it'll shoot it up. And so this little cannonball will have a horizontal motion because of the movement of the cart, but the cannon will give it a vertical, and I'm trying to convince you that the horizontal and vertical motions will be separate. And so even though the cannonball gains a vertical speed while it's being pushed, then it loses a vertical speed because of gravity, then it falls down, all of that vertical motion is independent of the horizontal motion, so it keeps the same horizontal motion. And so when it fires, it doesn't just go like this, it goes, and it keeps It's horizontal motion. In fact, better still, so does the cart. So where does the ball land? In the cart. And that's worth probably seeing again. What is the position on the x-axis? It's unaffected by the motion on the vertical axis. If I give myself perhaps some more room so I can push it faster, it still works. That is, where does it land? In the cart. Because the horizontal motion is completely separate from the vertical motion. That's how nature behaves. So I'll say it again, knowing that that's how nature behaves. We can then justify the start of this chapter by saying, here's what we're going to do. We are going to think, we are going to solve problems as if the x and y motion are separate and independent. Because, of course, they are. That's why I wanted to run those two experiments and have that discussion. All right, so keeping that in mind, we might then change, or maybe I should say increase, what we did in the last chapter, and that is on our grid, if you will. I'm going to put an x-axis and a y-axis now. And things are not going to just move on the x-axis like they were yesterday, but they're going to move x and y. Was that a question or just?
I was just asking, when you're just throwing a ball,
Yeah.
is that going to be one-dimensional, two-dimensional, or three-dimensional?
I would call it 2 because it goes across in the x direction, and of course it goes up and down in the y direction. It doesn't really go in the third dimension, unless maybe the wind was blowing, right? So if I were to throw something like this that was like a ping pong ball, and the wind was blowing here, this ball would go up, and maybe the wind would take it over here. So then it would be a more realistic problem where it would move x, y, and z.
So it's going to be straight.
But without the wind, it's just going to go straight where I threw it.
If I throw that ball from here to over there, is that going to be three-dimensional?
Again, I would call that just 2 because then I would put my x-axis where you're throwing it, and it goes up along the y-axis, and so I only have to worry about the 2 dimensions. Of course, if you kind of were thinking that you're going to call this the x, and then this the y, and then this the z, then okay, then you're thinking 3 dimensions. But you're also thinking it harder than it needs to be, because it's just moving in a plane. And so my advice would be keep it simple, right? Don't set up your grid to make things harder on you. These are hard enough, right? However, with that said, I will point out that the subtlety lesson in this chapter is how would we solve a problem in 3 dimensions? We would do 1 dimension twice, 3 times. And so kind of a indirect lesson here is really how do you do 3 dimensions? But it's going to be hard enough to do 2, so let's just focus on 2, okay? That's one step at a time. Okay, so back to this grid here, we're going to then have, some kind of positioning of it, and let's just say we're going to then throw an object. I could maybe throw it straight along the x-axis. I suppose I could throw it in a combination of the x and the y-axis. I guess I could just throw it straight up in the y-axis. Wouldn't all of those give me a slightly different result? Because they're different directions? Do you remember our discussion about vector versus a scalar? So the throwing, the initial velocity is a vector, right? It matters how, not only how much you throw it, but what direction, right? If I throw it just horizontally that way, I get something different than horizontally that way, which is still different than if I throw it vertically that way, which is still different than if I throw it at a 45. And most people know it'll land at a different spot based on how hard I throw it. But I want to just overly emphasize it also depends on what direction I throw it. So this is a vector. This is a two-dimensional vector. So I want to take a few moments and say, let's look at just direction in 2 dimensions in general before we really get into our kinematics. And I like to do that by maybe giving myself a little bit of space here. Maybe I'll put it over here. And maybe use this stage as 2 dimensions and say, what would happen if I took maybe 4 steps in the x direction? 1, 2, 3, 4. And then I turn 90 degrees and take 3 steps. 1, 2, 3. Where am I? How far am I from my starting point? Or put another way, couldn't I have gotten to that same spot by starting here and going at some angle and taking a certain number of steps and got to the same place? So our thinking is going to be this, that if you take a length of 4, and I won't put any units here because this is 4 steps, and I don't really, they're not a meter, they're not a foot, I don't know, they're steps. Okay, so I took 4 steps, but then I took 3 steps. You might say, well, technically you did 2 little hikes. Okay, but I want to ask you, what would that be equivalent to? Yeah, and so some of you are seeing, wouldn't this be Pythagorean's theorem? Right? Wouldn't this just be simply saying that you have a length here, I'll call it C, because Pythagorean theorem says if you have a right angle triangle, okay, that's what I did. That's why I turned 90 degrees here on this first one. The sum of the square of the legs equals the square of the hypotenuse. It's that a squared plus b squared is c squared. All right, so if this is one of the legs squared, and this is the other leg squared, that should equal the hypotenuse squared. And so 9 plus 16 is 25, which then taking the square root makes a distance of 5. So I'm going to say that instead of thinking of this as 2 little hikes, where I go 1, 2, 3, 4, turn 1, 2, 3, I could say this is really the same as if I had gone 1, 2, 3, 4, 5. And of course, another part of this is what angle. All right, so how do I find that angle? You guys in class, help me out here. How do I do it? All right, so now we're going to dig out some trig. Yesterday we dug out some calculus. Today we're going to dig out some trig. Okay, and hopefully you remember the tangent function. What is the tangent of this, say, unknown angle theta? What's the definition of tangent? Yeah, opposite over adjacent. So looking at this angle, the opposite is 3. The adjacent is 4. Getting my calculator, I can then say, what is the angle? And so using my calculator, I will do what's called the arc tangent of 3/4, which should be the famous 37, because this is the famous 3, 4, 5 right triangle. Let me just give it a try. First of all, let me check, am I in degrees or oh, no, I'm in radians. Let me switch to degrees. Okay, then let me go inverse tangent of 3/4, and I come up with almost 37 degrees. A little more accurate is 36.9 degrees. All right, so here is the reverse. What if I had changed this? What if I said, instead of doing 2 little hikes, I'm going to do 1 hike. I'm going to turn 37 degrees and take 5 steps and only do 1 hike. Don't I end up in the same place? So this is going to be our goal today. You can think of this as 2 pieces, one along the X and one along the Y, or you can think of it as 1 piece along a diagonal. Aren't they equal to each other? And so what I want to emphasize to you is sometimes we will think of it as its total magnitude and angle. You might call that a polar coordinate, right? How big is it and at what angle? Or we might think of it as how much along the x-axis and how much along the y-axis. Let's keep working with this. This is worth spending some time on. Because what I'm erasing here on the board and try to emphasize to you is nature treats the X and Y motions separately. So if I were to toss a ball up at an angle, instead of thinking of that as one velocity, I could think of it as a velocity on the X and also an initial velocity along the Y. And so that's why our problems, we will always start off by saying, okay, the initial velocity may be 5 at 37 degrees, but that is really equal to a 4 along the x-axis and a 3 along the y-axis. That's what I'm getting at. Let's do some more of these. And you'll see it better when I start getting into some examples. Yeah.
How would you know the value for theta without doing it 2 steps?
Two steps?
You know how you did like the quadratic formula and then use trig functions to find the angle?
Oh, okay. Yeah.
How would you, just if you were to say like, I want to do 1 hike as opposed to 2 steps?
Okay, so, all right, I'll tie your question in to this next kind of example, and it's really kind of the same thing, but it really needs to be said twice because it's kind of hard to digest here. But what I'm trying to say is you could think of this little arrowhead as, and I erased it, a magnitude and a direction, or an X and Y. And so let me just do this. Let me say that I start in this corner, I turn 60 degrees, and I take 7 steps. Or you could say, I took, and I don't know what the number is yet, I'm going to work it out. I could say I went along the x-axis so many steps, and then along the y-axis, so many steps. Okay? And I think to answer your question, you have to either be given the magnitude and direction, so you can get what we're going to call the x and y components, or the other way around, you have to be given the x and y components so you can get its magnitude. I want to keep pointing out that both of these are equal. Both of these are equivalent. And what I just did a moment ago is I gave you the x and y and asked what the magnitude and direction would be. So let me reverse it. Let me give you a magnitude and a direction and ask you what would be the x and the y. Okay. Maybe it helps to then draw the resulting one on here, because we know that that total distance is supposed to be the 7, the hypotenuse. And this is supposed to be the 60. And so let's just say I want to find the x component first. How do I do that? Right, and so I'm going to use the trig functions. Now, I already used one called the tangent, which has to do with opposite and adjacent. But if you look at this one, I know the hypotenuse, and I'm looking for the adjacent. And as I heard somebody say, that's the cosine function. So that would mean cosine of 60 degrees would be x over 7. And then as I rearrange this, I would have 7 times cosine of 60 degrees. And I picked an easy one for me because if you don't remember, cosine of 60 is the famous 1/2. All right. So it's 1/2 times 7, which comes out to 3.5. So 3.5. And by the way, no, you don't have to remember that. Just grab your calculator. So I'm going to grab a calculator. I'm going to go cosine 60 degrees, hit enter. There it is, 1/2. Okay? Now, let's also say I wanted to find what that is equivalent to in the y motion. Now, I'm looking at this problem, and you could even pretend I don't know the x. Obviously, I do, because once I know the x, I could use any of the trig functions. But if I didn't know the x first, I'm looking at opposite and hypotenuse. Which trig function is that? That's the sine. So I'm going to say sine of 60 degrees would be y over the hypotenuse. Which of course means then y is equal to a 7 times the sine of 60 degrees, which that, what's that, root 3 over 2, 0.866. I'm going to use my calculator on this one. Okay, so I will go sine of 60, yeah, there it is, 0.866, and then multiply it by 7, and that is the 6.06. So this distance up here must be 6 point, I'll just round it to a 1 to make it simple. And so again, let me just overly emphasize, hopefully not too slow here, but we've got some trig to do to understand two-dimensional motions. Because what we have to do is either A, think about it as a 7 at 60 degrees, or B, think about it as a 3.5 in the x direction and a 6.1 in the y direction. And sometimes this is better, but sometimes this is better. And so what I'm trying to say is they are equivalent to each other. You can think of them either way, and whatever is the appropriate way of thinking about it to do the motion is what we need to do. And so I'm trying to show you, you will get some problems where they give you X and Y, and you have to find magnitude and direction. Other times, you will be given magnitude and direction, and you have to find X and Y. And so I wanted to start here with a little math saying, hey, we need to go back and forth, especially since I already told you that motion in 2 dimensions needs to look at how much is X and how much is Y. So there's a very good chance that the first step of every problem will be this. You throw it at 7 at 60 degrees, and the first step you have to do is figure out how much speed is that in the X and how much speed is that in the Y. And so you will see when I get into examples, this will be my first step. Change what is given to me as magnitude and direction into how much is in the X and how much is in the Y. You've been patiently waiting, yes?
So, like before, you were showing it in like steps, like those magnitudes.
Right.
But they can be like acceleration.
Ah, very good. Very, very, very great question. Notice that I was showing, as you said, in terms of position steps. But this is going to be extended out to be true for anything that has direction, so any vector. So this would be true not just for position, which is how I'm trying to illustrate it because I think it's easy to understand that at first, but we're going to translate that into speed, as I was kind of alluding to when I said you throw something, but we're also going to change that into acceleration. We're also going to change that for forces, and so any physical quantity that has directions will go through this step. And I'm going to illustrate it here at the beginning with position because that's the easier one to understand. But then don't be surprised as we move forward into the next chapter where I say this. One person pushes in the x-axis with a force of 3.5. A second person pushes in the y direction with a force of 6.1. What are those two people equivalent to? And so you will be given the x and y, and then you will come up and say, well, those two people is the same as if one person was pushing with 7 at an angle of 60 degrees. So yes, it works for acceleration, it works for velocity, it works for position, it works for force, it works for any vector. And to be honest, that's really going to be your mathematical challenge here this chapter and next, is doing this conversion from either x and y to magnitude and direction, or magnitude and direction to x and y. And I think one more harder example is worth the time. How about we do something like this? What if I say, I'm going to start here at the origin. I will turn 20 degrees and I will take 11 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So 20 degrees, 11 steps. Now I turn a little more. So I was turning 20 from straight across. Let me turn now so that I'm 70. And now let me take 7 steps. 1, 2, 3, 4, 5, 6, 7. What is this equivalent to? All right, so it's probably worth drawing before we try to get into the math. And so when we work with problems involving vectors, you're going to see me draw a bunch of arrowheads. You've already seen that. It really helps your thinking process because when we try to represent the physical world, not only is the magnitude important, but the direction is important. And so let's do this. Let's draw the length of the arrowhead to represent how big it is, and we'll draw it in the direction it actually is. And that's why visualizing this as position is the easiest. Even if we have a vector that is not positioned like force, we'll still draw it on a blackboard or whiteboard or piece of paper. We'll draw it as if they're position vectors. Because again, it's easier to see with position vectors, but they still work. And I'm so glad you asked that question, with force vectors, acceleration vectors, and velocity vectors. So I'm going to draw it as a position, and I'm going to say this. Here's what I described. I described starting here, turning, and I said 20 degrees, and I said 11 steps. So let me put a little 11 here. So I'm going to draw this, the equivalent of 11 something, whatever 11 steps are. And it's at 20 degrees. And then I said, when you got to this point right here, turn a little bit more, and so I'll just kind of put a horizontal dotted line. Oh, now what did I say 70?
You said 70.
70? Okay, so let me turn a little bit more. So now this is 70 degrees. And I said 7 steps?
Yeah.
Okay, thank you. Glad you're taking good notes there. Okay, all right. Now, to make it stand out, I'm going to draw it in red. I think you can see when you do the drawing that the equivalence of these two would be that red one, right? You could say that, okay, instead of doing this plus this, instead of doing 2 little hikes, we could just do 1 big hike. And so my question is, how long would that hike be, and at what angle would that hike be? Okay. Well, maybe using a couple of other colors on here. Can you see that this first one, if I draw it in green, even though you might say it's 1 hike, the first hike, we could think of it as 2 sub-hikes. We could think of it as an X and a Y. In fact, to put some notation here, we like to do this. We like to say if the first hike is called A, and because it has a direction, we put an arrowhead over it. We can then say that A really has a little subpart, AX. It had a certain amount of distance on the x-axis, but it also had a certain amount on the y-axis. Now again, maybe to make it stand out, let me draw it in orange. Let's look at the second little hike. The second little hike would have a little piece across here and up here. Maybe I'll call this vector B. So vector B has, a length and a direction. So I'll call it B. I'll put a little arrowhead indicating it not only has a number, but it has a direction. But I can then label it as thinking of B as being so much along the x-axis and so much along the y-axis. Well, switching colors one more time in the blue. Can you see that the equivalent of those two? And so I'll take this red one and say this red one has, and a lot of times we call it R for the result of the two. So if I call this an R, this would be R going up, so R sub y, and this would be R sub x. And can you see in this little picture that r sub x would really be the x pieces of the two put together? And they have nothing to do with the y? And so the phrase I like to use is to figure out the result of two vectors, put x's together. Put x's with x's and y's with y's. And so these two little hikes, A and B, each have an x component. And so the total result would be the x of each of them. And then what, of course, would happen over here, what would be the result of the y? Well, we would have how much did it go up during the first hike? And then how much did it go up during the second hike? And so we can get the x component of the result by putting the x's of A and B together. We can get the y motion of the result by putting the y's together. And now we can use that trigonometry that we've been talking about for the last 20 minutes or so and do the math on it. So let's try the math here. So why don't I start with the hope of getting AX. See, this first little hike, which I've called A, is 11 long at 20 degrees. So this is the hypotenuse, and I want to know the adjacent. That is the cosine function. So I'm going to write here cosine of 20 degrees would be AX over 11. Meaning AX is 11 times cosine of 20, and that's going to give me my first of my four numbers to get. Okay, so cosine of 20, enter, and then times 11 gives me 10.3. So conceptually, I'm saying that this little hike of 11 is equivalent of going across 10.3 and then up a little bit. And let me find the up a little bit, because I can do that with the sine function. Right? The sine of 20 degrees, so sine means opposite, so that's AY over 11. So AY over 11. And so let me just take my calculator and go sine of 20, and then move this over to here, go times 11, and I'll save a step by not writing it out, but I'll get 3.76. So I hope, even though I'm not done, you're beginning to see that to figure out how long the result is, I don't just take the 11 plus the 7, do I? It's not 18. It's kind of bent there in between. And in order to figure out how long that is, I have to then take magnitude and direction and change it into x and y components. That's what I'm trying to illustrate. Now, let's go ahead. Oh, and I guess I meant to color code those. I should have done those in green. My bad. So this is all the calculations for the green one. That's the first one. And the orange is the second one. So let's go ahead and look at that one. So kind of looking at this triangle here, to get the x component, I would want the 70 degrees, and I would want the trig function cosine. So cosine of 70 degrees would be bx over the hypotenuse, which is 7. And so bx is, well, let's see, cosine 70 multiplied by 7, and I get 2.39. If I do the sine of 70, All right, so coming back over here to this little picture, sine of 70 is the opposite, so that's by over the 7, which means by is, and then so I'll go sine of 70, and then multiply by 7, and that would be 6.58. Now, sadly, you can see that trying to figure out how far this hike is really a lot of work. You got to break it down to its x and y components, and then we got to put them together and do the Pythagorean theorem still. So I still got a lot of work to do, and I've already done a lot. But that's the way nature is. Like I said, if we don't get to decide if nature is going to be easy or hard. That's the way it is. But I think looking at the visual picture, you can see why I'm doing all of this, why I'm changing a magnitude and direction into x and y, because to figure out how far it goes on the x-axis, I got to put x's with x's. So I got to figure out what the separate x's are. And so now, if I stick to my color code here, blue, I can finally say, what is Rx? Because Rx is the AX and the BX added together. And so the AX, we said, was the 10.3 steps. And the BX right here is the 2 points, and I'll round it to a 4. And so when I add these together, I get 12.7. And so what I finally have learned after all of this is the total movement on the x-axis is 12.7. And that's this piece right here. It's a combination of the x for the first vector and the x for the second vector. And of course, let me do the same thing for r sub y. This would be the ay plus the by. And so ay is the 3.76, and the by is 6.58. And if I add those, let's see, 14 carry 1, 12 carry 1, 9, 10. And so I can come over here and say, okay, what I've learned so far is that this vertical part of the resultant is 10.34, and the horizontal is 12.7. So finally, can you tell me what our vector is? Because it's going to have then a magnitude and a direction. And so those two little hikes each had to be thought of as separate little hikes, x and y for each of them. So we can put x's with x's and y's to y's. Now we can finally do the reverse of this. How do you get the magnitude? Well, there's our Pythagorean theorem, right? We've got the two x pieces, the x piece and the y piece, so we will then use Pythagorean's theorem to get the hypotenuse. How big is r? So I'm going to put the x, 12.7, and square it, and the y, 10.34, and square it, and then take its square root. And then to get its direction, like you saw me do a while ago, how would I get the direction of the resultant? And so maybe I'll put an angle right there. And maybe you can see it better if I put the vertical blue one over here and the horizontal blue one over here. But wouldn't that be the opposite over the adjacent? And the opposite is the ry. So this would be the ry over the rx. And the ry is the 10.34, and the rx is the 12.7. Quite a few steps. So, but the lesson here is we can think of it as either way, whichever we need to do. And in this case, I said what we need to do is we need to take a little hike where we gave them the magnitude and direction. We needed to break it down into x and y for both of those little hikes. Because in order to combine them together, we have to put x's with x's because they act independently. And so the way the problem was given with magnitude and direction, we have to break it into its x and y's. There was no other way to figure how long this thing's going to be. So sadly, it's going to be quite a few steps. But hopefully they're logical steps. And so x goes with x and y goes with y. Okay, so finally I can get to what I want to know, which is how long is this? All right, so this is 12.7 squared plus 10.34 squared. I'll just go enter, and square root of all of those. And I get a total distance of 16.4. And what that would mean then is I could think of this motion as just being one equivalent motion that is 16.4 long. And so this 11 plus this 7 makes 16.4. Try that on a 5th grader. What does 11 and a 7 make? 16.4. Everybody knows that, right? So 11 and 7, if they were just scalars, right? If they were just regular numbers, you would go 11 plus 7, and you'd go 18. And that's what you would do with regular scalar numbers. But when the direction isn't part of it, oh, it got a lot harder. And that's the first part of this chapter, to illustrate. We got to think about vectors. We got to think about directions. To do that, we got to think about the components. So I would say then, you can think about this as one hike being 16.4 at an angle of, so let me go inverse tangent of 10.34 over 12.7. 39.2 degrees. And I'll say it one more time before we jump into examples, just to keep overly illustrating this. Either way of thinking of it is exactly the same. You can think of it as somebody took one hike, turned 39.2 degrees, and took 16.4 steps. That's what these two are equivalent to. You could also think of it as we started. Somebody does A first, so they turn 20 degrees, take 11 steps, turn and do 70 degrees, and take 7 steps. So you could think of it as 2 hikes. You could even think of it as 4 hikes. You could say somebody starts here and on the x-axis, and so A sub x goes 10.3 steps along the x-axis, and then I'll look at AY, 3.76 along the y-axis. Those two are equivalent to the A. And then they did BX, 2.39 this way, and then BY, 6.58 that way. So think of it as 1 hike, think of it as 2 hikes, think of it as 4 hikes. They're all the same, they're all equivalent, and we need to think about it one way or the other depending on what we're asked and how we're trying to work it out. And so hopefully this, I'll call it the grand finale, doesn't look too scary, but if it does, know this we just did a really hard problem. We did kind of the tip of the iceberg, the top of the mountain here, in order to get us ready for some really hard ones. Yeah.
So the vector, so the 16.4, that would be the magnitude or the
Yeah,
direction?
that's the magnitude.
And then the direction would be the theta.
Yeah. Yeah. In fact, maybe I'll put that directly on my graph here. And so the length of this red one is 16.4. And then this angle right here would be the 39.2 degrees. And what I want to do, and of course, since this is pretty advanced, let me encourage you, make sure you read this part of the book. Your author, in the first 2 sections of this chapter, that's what he does. He says, let's look at these graphically and let's look at these analytically. I think you need to do both at the same time, because when I draw a picture, this helps me think about which trig function do I want. Do I want a sine? Do I want a cosine? Which angle to look at? Also, looking at the picture really helps me understand why I have to break it into x and y. Knowing that I got to put x's with x's and y's to y's makes total sense when I see this picture. Also, this picture makes total sense why I got the magnitude by using the Pythagorean theorem, because what I really found was how far is it in x and how far is it in y, and so Pythagorean's theorem is the resulting hypotenuse of both an x and a y, a leg and a leg of a right triangle. And so all of this stuff, I don't have to memorize what steps to do, and that's what I really want to emphasize. Not memorizing step by step what to do, but to stand back, draw a picture, and use that picture as your guide to decide which trig function to use, when to use Pythagorean theorem, when to do the inverse tangent function. And that way, there's not this overwhelming look of a recipe of steps that you have to do. Okay, well, as I said, I wanted to spend a long time, and I did, going through a bunch of math to really allow us to do some of these two-dimensional problems. And since 2 dimensions is just 1 dimension twice, and we've already talked about doing 1 dimension, I think we're ready to actually start doing some examples. You might even say, hey, we're done with the chapter. Do you want to know the answers to all the homework problems in this chapter? I'll put it back on the board. If you want to know position from velocity, you just integrate. Or if you have position, you take its derivative to get the velocity. Or if you have velocity, you can get acceleration by taking its derivative. Or you can integrate it and get its velocity. And now I'll say do that twice. Do it once for how does it move on the x-axis, and do it once for how it moves on the y-axis. But here's going to be the harder new step. When you begin a problem, the first part of it might say you throw a ball at 20 degrees with a speed of 11. So your first step is to ask, what is the speed in the x direction? So you have to do the cosine function before you can start doing your one-dimensional motion to figure out how much of the initial speed is accredited to just the x. And then you'll have to do the same thing for the y. You'll have to say how much of the initial speed is credited to the y motion before you can do this one-dimensional motion stuff. So that's why we spent a long time looking at our trigonometry and our angles and combining them together. And that'll take a couple chapters to sink in, I realize. But it'll help if we just start doing some examples. All right, So let me turn on the display. Let me go here to your textbook. Let's me see if I can find the chapter 3 homework problems. And let me look at my notes. I scribbled up here that number 20 looked like a good one to start with. So I will do number 20. And in chapter 3, right?
Oh.
I think I clicked on 4 so I could go backwards. It was quicker than trying to scroll through number 3. Yeah. So this first one, again, is not one with motion yet. It is really kind of an example that I just did, is trying to say, hey, let's work with some vectors. You gotta learn how to work with vectors before you can start doing this two-dimensional motion. Okay, and the reason for that, as I said, is because you gotta break it down into its little pieces here. So I think number 20 is going to be a lot like the one we just did, and then maybe that would be a good time to take a break, and then we will come back and actually do motion ones here. But number 20, and let me make this a little bigger and readable here. Is that big enough? What's 150% do? Okay, maybe that one right there. And so number 20 is over on the right-hand column, gives a nice little picture, and that's very helpful. And it says this: a new landowner has a triangular piece of flat land, and she wishes to fence it. Okay? Now, look at this picture, because this picture is kind of helping you see the description here. It says, starting at the west corner, and so here is our XY grid, and we're just going to put a little compass rose with the standard north going up for the Y, south going down for the negative Y, east going positive X, west going negative X. Okay, so here's our compass rose. Here's our grid. We're going to start here on the west end of our lot. And so she measures the first side to be 80. So there's vector A. And so we're looking at vectors. We're looking at position vectors. Like I said, that's the place to start. They're the easiest to see. All right, so it's 80. And so she measures the first side to be 80 meters long. And the next one, so B right here, to be 105. So writes 105. These sides are represented as displacement vectors A and B in the figure. She then correctly calculates the length and the orientation of C so that it gets back and encloses her triangular plot of land. And so basically it's saying, what is the length of that? Now, they're going to help you out here because this problem has 3 vectors, so it's one step above what I did. But did you notice vector A plus vector B plus vector C would equal what? Right, and did you see how in my picture I drew from where you started, and as I drew them head to tail, head to tail, head to tail, then I drew it to where it ended? So, in other words, if I draw 3 vectors, head to tail, head to tail, head to tail, which is what we have here, what is the length from where you begin of the first one to where you end of the last one? Isn't that 0? And so a piece of this is to say that if you're going to add 3 vectors together and it encloses, that means it comes back and the end touches where it began, the length of those 3 is a total of 0. Fair enough? Now, let me also emphasize this. didn't we just do the problem that said you take the x component of A, the x component of B, and the x component of C to get the resulting x component? Which would be what, by the way? 0 for this one, because we get back where we started. We want to say that after this vector moves x, and this one moves x, and this one moves x, the total of all those 3 x's is 0. On the x-axis, you get back where you started. Remember that phrase I was saying, treat the x's and the y's separately? And that's what we're going to do. We're going to put all the x's together. There's 3 of them this time. And we're going to put them together, but we realize they got to get back where you started. And so that's the hint, really, what they're giving in this problem here is A plus B plus C has got to be 0. Okay, but it's also the same thinking in the other dimension. That's why this is a two-dimensional problem. What would you say about AY, BY, and CY? Of course, that's the resulting y of the 3 together, but what should it be equal to? 0 also. See, so this little equation, which we call a vector equation, is really saying the x's have to add to 0 and the y's have to add up to 0. We treat them separately and they each have to add up to 0. To get back where you started, you have to have a 0 net motion in the x, but also a 0 net motion in the y. Fair enough? So now let's break these into the separate pieces. Let's just focus on how would you get A sub x? Oh yeah, this one is actually given. We have a length and we have an angle. And so if you look at this triangle right here, this x piece right here would be related to the adjacent. That's the cosine function. So I would say here, cosine of 21 degrees would be ax over its magnitude, which was what, 80. Now, I'll work out the math in a minute because I don't think the math is much of your challenge. Although if you don't know how to use your calculator, please ask and I'll explain. But how would I get AY?
You do sine 21?
A sine. Yeah. And I'm glad you say that, but this one is going to take you back to your math class. Is it sine of 21 or is it sine of negative 21?
Sine of 21.
Oh, good. And somebody's saying it could be looked at either way, and I totally agree. The downward angle in a math class is usually called a negative. That's why I'm even asking it. Negative 21. And then what that would give me is a negative downward motion. But others of you, and you were just looking at its magnitude, but remember it's going to have then a negative in it. So why don't I do it where you brought it up? I'll just do the positive 21, but keep in mind then that if I do sine of 21, then what we're talking about is the size of AY. AY goes down. Did you see that in the picture? So I want to make sure when I start putting AY into this equation here that I have a negative number. And if I forget that some of these are negative, there's no way I can take 3 positive numbers and add them together and get 0. So some of them have to be negative. And so you could either put negative 21 degrees, and then the calculator will give you the negative answer for it, or I think it's better to look at the picture. And so I'll do the magnitude of it and say, well, it's down, so of course it's going to be a negative number.
Can we just get the cosine of 69 instead of that?
Yes, yes. And so remember, your trig functions are complementary. So if you want to go sine of 21, that's the same as cosine of 69. And it really depends what angle you're looking at. In fact, what you're asking comes up right away with angle B. So let's have that discussion in just a moment. Okay? But let me actually then set this up. So I'm going to go sine of 21 degrees and say that's going to equal the magnitude of AY over the 80. Now let's move on to vector B, and this is going to come up with your same question. How much of B is in the x direction? And see how they give you an angle of 11 degrees? But that is not measured from the x-axis. I bet in your trig class, and even today, you were saying, well, if I want the x-axis, I'll do cosine. And if I want the y-axis, I'll do sine. But it doesn't always work that way. It only works that way if they give you the angle measured from the x-axis. That's not what they did here. You could change that and measure it from the x-axis, but let's not, because I think we can see the picture better if we use their 11 degrees. In fact, I'll even draw it over here. I'm going to switch to a color red and say, I'm looking at B, and I'm saying this is a vertical piece of B, and this is the horizontal piece of B, right there. And in here is that 11 degrees. So using red here, if I write cosine of 11 degrees, cosine means what? Adjacent. Not x. Adjacent. X and adjacent would only be the same thing if you measured from the x-axis. We are not measuring it from the x-axis. And if you look at this triangle, the adjacent piece is BY. And that's what I and the author wanted you to see in this problem. And what you were getting at is we could switch it from 11 degrees to what's 90 minus 11? 79 degrees. And instead of using then the cosine of 11, we could do the sine of 79. But I'm going to put here BY over its magnitude. So what's the magnitude of this one? 105? You're looking at me like I'm crazy. Did I miss something?
So the B that we're reading is going to be the line of the triangle that's placed, right? So that would be the hypotenuse of the BY, right?
Yes. So the hypotenuse is 105.
Right. Oh, okay. Yeah.
So, okay, good. Yeah, so that's why, yeah, right. So I put the hypotenuse in the bottom, right? Okay, yeah.
And what was the other part you're talking about, the 79 degrees? Get that?
Oh.
It's like perpendicular.
So you could look at this angle, which is 79 degrees. And that's measured from the x-axis. And you might say, well, it is the sine of 79 degrees. That would give you the y component. And I'm going to say, yeah, the y component is what you get if you measure from the x-axis. So if you want to switch it and measure from the x-axis, you got to use the 79 degrees. Then you can use the sine function to get the y component. They're going to reverse because they're complementary functions if you start measuring from the y-axis. Oh, shoot. Thank you, Ron. This would be the 79 because it's actually tilted like that.
So how do we know that that would be a right angle there?
Because I'm doing an xy axis.
Okay.
I'm looking for x and y components.
Okay.
Right. So yeah, and so it's a grid, and x and y grid is 90 degrees. Mm-hmm. So I like this one because it gave me a chance to say, you have options here. You can leave the 11 degrees as they've given it. You just got to make sure you recognize that the cosine means adjacent. It doesn't always mean x. Or you can switch it back to measuring the angle from the x-axis and use the traditional sine for the y. Kind of your choice. And maybe I'm giving you too much choices, which can make things worse. But I personally, for this problem, like this one because they give me the 11, so I'm going to focus my attention on the 11. And they also, you know, I can see right away that it's the y component that is adjacent. Adjacent goes with the cosine function. And so if I focus my attention still on the 11 degrees, if I go sine of 11 degrees, and maybe coming over to this picture, sine of 11 degrees, remembering that sine means opposite, so this would be the opposite, so this would be the x. By the way, do you see how the x is heading back, so it's actually a negative number? So I suppose I should be a little careful here and say it would be the magnitude of it, and then over the hypotenuse, 105. If you would rather look at the 79 degrees, you can. Nothing wrong with that. You're looking at this angle here, 79, and it's measured then from the x-axis. Actually, it's really measured from the negative x-axis. But then you can do the cosine function, and that would give you the magnitude of ax over 105. Bx. Thank you. Bx. Yeah.
Wait, so why is bx negative again? Because, like, how do you, because was it ay? Yeah, ay was, so it was moving.
I'm going to answer you from this picture.
Yeah, okay, it's moving up.
See how this is going up and left?
Yeah.
Left is negative.
Okay.
Mm-hmm. So the y component is up, so the y component is positive. But the x component is negative. And maybe I should have spent more time over here saying, look at vector A. This is saying to the right and down. So the right is positive x's, and down is negative y's. All right, so this is the hard part of the problem. Now it's pretty simple because we already said you add these three to get 0. You add these three to get 0. So we can get out our calculator now and actually then solve for, say, ax, where's my blue one? And we can then say that is an 80 times a cosine of 21. So that is a 74.7. We could solve this for ay also by saying, all right, let's take the sine of 21 and multiply it by 80. And that by itself would give me the absolute value of y. So I'm going to put a negative myself in here. It's not on my calculator. I'll put the negative, and that would be a 28.7. And so just to repeat what you just said, here is what it's saying about A. A is saying go right and go down. So we got a negative number for the y, that's down, and we got a positive number for the x, that's right. For B, changing colors here, by, okay, would be this, cosine of 11 times 105. And that would be 103.1. And then bx, using this, would be sine 11 times 105. And my calculator says it's a 20.0 with a positive number, but remember, I had purposely looked at the picture to see that this was a negative, and it's probably worth saying it again, coming back to the picture. The B is an up, so that's a positive y, but it's also a left, so it's a negative x. So I've got the negative x and the positive y. All right, so knowing those, I can come back into each of these equations and actually then figure out what the C sub x is, because the A sub x is 74.7. The B sub x is a negative 20.0. And so since that equals 0, let me take the 74.7, let me subtract the 20, let me move it to the other side, and that's a negative 54.7. Now look at the negative. The negative means it must go left, and sure enough, vector C in this picture is going left and down. So I expect the x to be negative because it goes left, but I also expect the y to be negative because it goes down. So let's see what I get for the y. Hopefully I'll get a negative number here. All right, so now let's do this calculation, equals. So A sub y is a negative 28.7. B sub y is 103.1. And now I can get C sub y. All right, so I'm going to go 103.1 and subtract 28.7. That makes 74.4. I'll move it to the other side, so it's a negative 74.4. Ah, good, negative. Right? So now, as the problem says, this landowner says she calculated it correctly, and we've got to find that length. So we're not quite done because we have the x and y components. Did you notice all this work we had to do? We had to put x's with x's and y's to y. Wouldn't it be so much easier if direction didn't matter? I mean, 80 plus 105 would just be 185. Oh, she needs a fence for 185 to close it up. No, the direction matters, right? It's real important. So that's why we have to go through all this and break down the x and y components. All right, with that in mind, we can finish now by saying that the total value of C, I'll call it C squared, is the x squared and then the y squared. Right? That's the Pythagorean theorem. That's going from components to magnitude. Because we've just spent a lot of time going from magnitudes to components, so we can put x's with x's and y's with y's, only to have to go back. And I wish there was an easy way myself. There's not. And so hopefully it begins now to make sense. And once you see the reasoning of why it makes sense, it's still a lot of steps, but you don't have to memorize anything. It's like, oh yeah, I just got to put x's with x's, so I got to go through my trig functions. Okay, so I'm going to take the x component, which is 54.7, and square it. I will then add that to the 74.4 and square it. I will then finally take the square root and get the final result of 92.3, and I think all of this was in meters. I haven't been writing any of the units, but we've been talking about the length in meters, and so we finally have the answer that if we want to enclose this, we need a fence that is going to be 92.3 meters long after we just put in fence A and B. Now we can close it with fence C. Two-dimensional stuff. It's a really good time for a break, maybe even a little late, but question, yeah.
So maybe I haven't done trig in a while, so could you not do like a function with like the 79 degrees to get C?
Oh, now, okay. I think what you're getting at is, yeah, in your trig class, you probably learned something called the law of cosines. And the law of cosines is really nice because it can give you the third side of a triangle. So if you know two of them, you can get the third side if you know the angle in between. You're absolutely right. However, it only works for triangles. What if this was a problem with 4 fences? 5 fences? 6 fences? This method of breaking down to x and y works for any amount. So I would say that if you remember the law of cosines and if you have a triangle, go ahead and use it. It's valid. But we don't emphasize that because it's limited to only things that have 3 sides and doesn't help us for, in general, all the problems we need to do, where this would work for any number of sides. That's why. All right, so let's take our 15-minute break and we'll come back at 10:05 and continue to do some of this, but actually now do some motion ones and actually. All right, hey, welcome back for the break. Let's do a bunch more examples, although it was pointed out to me on the break that there was one step I didn't quite finish. I just got the length of the fence and I didn't do the orientation of the fence. So at least let's mention that as we close up here. And so you'll see here in this picture, they talked about this angle going down from the x-axis here. So maybe at this point I will maybe redraw, no, maybe I'll just do a color in, not blue, green, and come over to here because we got the length of the fence, this 92.3. But now maybe we should think about this fence as being so much in the x direction, so that's the cx, and then so much in the y direction, that's the cy. And we're asked for this angle right here. Let's call that angle theta. And of course, they could have done the orientation from a lot of different orientations. They could have done the angle within the property instead of outside the property, or maybe even down here. But that's what they chose, so I'm going to go from that angle. And then if you will notice that if you write the trig function tangent of theta, remember tangent means opposite over adjacent. So the opposite of this angle is cy, and the adjacent is cx. Now we're kind of back to our discussion we had here, where we can think of them in our minds just as positive numbers. How long are they? Because if you remember, we got a negative value for cx and a negative value for cy. Oh, but I'm just going to, in my mind, think of this in terms of absolute values. That way when I do the inverse trig function, I get that angle, and I don't have to worry about the pluses or the minuses associated with the trig functions. Although in this case, it wouldn't matter because the trig functions technically from your math class are measured from the x-axis. So that's what I have here. And so I would be okay, but I just want to keep having you think about the physical picture, because this physical picture where you think about positive lengths will be very powerful in the next few chapters. And so I just want to think about absolute values, just how long is it. So instead of writing a negative CY, I will put a positive 74.4. And for the CX, I will put a 54.7, so that then I can grab my calculator here and go inverse tangent 74.4 over 54.7 and come up with 53.7 degrees to finish it. And so again, we spent a lot of math time here, but I think important time, because for some of you, I think it's probably been a while since you've been working with your trig functions. And that's the necessity of breaking down some kind of vector, you know, off on the xy plane and breaking it down to say how much is x and how much is y. So we'll keep doing that. Now let's go into some examples that I think are really more appropriate for what we're doing. This is kind of preparing you for the math you need to get ready for the motion. Number 25, I think, is the first one on my list that is actually involving motion. Yep, there it is. Projectile motion. All right, let's talk about this one, because there's a couple things I want you to see, and so it's kind of both a lecture and an example. But I've been saying here during this whole lecture that we're going to treat the x and y separately because that's how nature treats it. So let me ask you this. What is the acceleration due to gravity again? Negative 9.8? Is that the y or the x?
The y.
Oh, okay, that's the y. So what's the x? And that's really what this is going to bring up. Watch, if I take an object here and I let it go, it accelerates in the y direction, right? And that's the lab we did yesterday, or you guys soon will online when I get it to you. And we measured it, right? 9.8. So I would say the 9.8 that we've been talking about was the y direction. But did gravity pull it left or right? It didn't. So what would be the acceleration left and right? The x direction. 0. So that's what this problem is really going to bring up here. Remember I said we got to do our x motion and our y motion separately. So when we talk about the acceleration, that really becomes two accelerations, one for the x and one for the y. And so I want to point out here in our first step that when they say you have a projectile, something that you toss across the room, you know its acceleration in the y direction and its acceleration in the x direction. The x is kind of boring, but I need to emphasize we know it and it's 0, and so we're going to use that in our equations. And so we're going to use a negative 9.8 when we calculate the y motion, and we're going to use a 0 when we calculate the x. And so that is a big step. Yeah?
So when the projectile is moving, its speed is not changing at all?
In the x direction. Ah, good. I'm glad you bring that up, because I was going to show you, and I'll do it now, a really neat video of projectile motion. Now, this projectile motion is a little video, and the reason we have an animation is because there's something in this video that I cannot actually do, unfortunately. See, this is going to be hopefully a picture of a ball being pushed sideways. And once it goes sideways, it begins to fall. So I want you to watch the motion of this one, but at the same time, there's a second object that is just dropped. And as I was trying to show you at the beginning of this class with these experiments, nature would treat them separately. So as this one drops, do you see that the vertical heights are the same? And that's what I was trying to show you with this drop ball experiment and this pop-up experiment, that it didn't matter that it had horizontal motion. But there's actually in this animation a third object that I can't do. What if I had a ball that was pushed sideways and there was no gravity? And that's what this top animation is. If there was no gravity, there would be no force, no acceleration, and it would just keep moving at the same speed horizontally. Same speed. That means no change in speed. That means acceleration is 0. Right? So constant acceleration means you are constantly changing your speed. 0 acceleration means you don't change your speed, or you might say you change it by 0 every time. And so I'll restart this animation, but the idea is that you will see that the horizontal one is straight under, or the real one is straight under the horizontal one that is supposed to represent no gravity and no force and no acceleration. So there is no change in speed in the x direction. There is a change in speed in the y. And that's because there is no acceleration in the x, but there is an acceleration in the y. And so, like I said, it's a pretty good animation showing this, but sadly, it's something I can't actually show you because I can't create that third object. I can only do the two, that one that goes sideways and down and this one that drops down, and that's what I did do for you. But I can't show you this one, but that's why it's there, to emphasize there is no horizontal in the x direction.
Is there like the reason why, or do we just say that because that's how nature?
Well, I'm going to do this. At this point, I will say that's how nature is, but as we get to the next chapter, we're going to go from just saying how it is to why it is. And we're going to say that's because gravity pulls down. There's a force down only, not left or right. And so it's this force that results in an acceleration. And gravity pulls down. And of course, you probably already know this, but this is not really a flat Earth. We don't live on a flat Earth, despite what you might read on the internet, where it is curved. So it technically isn't completely straight down, but more on that later. But on a small scale within this room, we could say the Earth is flat, and that's kind of what we're doing here. Yeah. Now, I'll keep playing this video because you actually see the next thing is what would happen if I fired, and I'll just pause it right here. And so it's the same thing, except instead of just giving it a horizontal motion, I'm going to give it an angled up motion. And so as you watch this one, it's going to follow along this path. And this ball right here is given the same vertical speed as this one has. So notice they're in the same spot vertically because they're each affected by that acceleration of negative 9.8. So they each slow down, come to a stop in the vertical motion, and drop down. But this one is the same idea. This one is given a horizontal speed as the same horizontal speed as this one. And since it has no acceleration, it just keeps going with that same horizontal speed. But notice that that's the same thing for the projectile. And that is kind of our little animation to show you, if I want to understand the motion of this projectile, I will break it apart into this and this. And I will do my calculations of y and my calculations of x separately, as I've been saying for a long time now. And so let me come back just a hair. Oh, that was a little too far. And kind of watch that. And hopefully that will help your mental thinking of why we are going to do what we do, and that is to then calculate the horizontal motion as if there was no acceleration, and the vertical motion as it was just going straight up and straight down. And so we're going to do one dimension twice, as you've been hearing me say. All right, perfect timing on that question, by the way. All right, so I will come over here and say, all right, let's look then at question number 25, which says projectile motion. All right, so it says a projectile is launched from ground level with an initial speed of 50 meters per second at an angle of 30 degrees above the horizontal. Now I'm going to pause right there and kind of encourage you to doodle a little bit. You don't have to be a good artist when we draw our pictures. Trust me, I'm the worst. If you think you're bad, know that I am worse. I don't draw well, but I can make stick figures, I can make arrowheads, and those little doodles really help with the thinking process. So I'm going to put a grid on here and say, okay, this object gets launched from ground level. So I guess one thing I have to do is say, where do I want to put my origin? Seems like, why don't I put it where the ball gets started, or whatever the projectile is. It just says a projectile is launched from ground level. So I'm going to call the launch point right here. Now, it doesn't have to be right there, but it seems like a good place to put it, because I can't think of any better place to put the origin. Now, that's not always true. Some problems there is maybe a better place to put the origin, but this is not one of them. Okay. Then it says it's at 50 meters per second and an angle of 30 degrees. So let me just kind of put that over here. I'll put a 50, and maybe I better put meters per second, but if I put too much on here, it'll get kind of messy. I do want to make sure I put the 30 degrees. And so what we've been doing for the last hour, hour and a half, is really saying, do you see how that could be thought of as a horizontal speed plus a vertical speed? And that's what we're going to need to do. We're going to need to ask, what is our initial horizontal speed? What is our initial vertical speed? We're going to need to separate it into what it's equivalent to. And that's why you heard me talk about, I'm going to go for a little hike, and I can think of hike 1 as really be made up of 2 sub-hikes, and then hike 2 is 2 other sub-hikes, and I put those 4 sub-hikes together to figure out the whole hike. That's exactly what I want to do. This may be described as one speed and one angle, but I'm going to start thinking of it as 2 speeds, an initial speed horizontally and an initial speed vertical. More on that in just a second. I'll even draw it. But let's keep reading here. It strikes a target above the ground 3 seconds later. All right. Now, if I was drawing a picture of its motion, maybe I'll even draw another one here. Its motion might go ding, 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 ding. And they don't really say if it strikes the target as it's still going up or on its way down, so I'm not real sure where to put the target. So just know I'm going to draw it after it's on its way down, but I don't know that. All right. I just know it strikes a target. Okay. So it strikes a target above the ground 3 seconds later. All right. So maybe I'll just put in t equal to 3 seconds to know, okay, it's been moving along for 3 seconds when it strikes this target. What are the x and y distances from where the projectile was launched to where it lands? Okay, my suggestion is to take your piece of paper, cut it down the middle, put an x column and a y column, because as I said, we are going to calculate these separately. X's go with X's, Y's go with Y's. Of course, they're tied together, so there is some information from the X that we'll want to transfer over to the Y, or the other way around. Some information from the Y that we want to transfer over to the X. So we won't forget that we have that ability to do it. But now we're just going to look at its position. So as I read that problem, and we think about what we did in the last chapter, you will notice that the thing missing is final speed. I don't know final speed, they're not asking for final speed. That was my clue to use equation number 2. So let me start with equation number 2. So equation number 2 would say x equals x naught plus v naught, and I'm going to add a symbol here. Initial velocity in the x. And this is why we spent all that time on the math. Is my initial velocity in the x 50? Well, let me pause right here and come back to what we were doing before the break. Maybe I'll use the green here. Let's look at this as being made out of 2 pieces, an x and a y. So I could do this. Cosine of 30 would be what? Well, it'd be adjacent, and that's what I'd like to do. I'm going to call this the initial velocity in the x direction. V0x. That's this new symbol. How much initial velocity does it have in the x direction? I'll say it again, it's not 50. So cosine of 30 would then be v naught x over the hypotenuse of 50. So the amount of speed, initial speed, in the x direction would be 50 times cosine of 30, which is 43.3. So that's why we're doing all that trig, so we can put x's with x's. Now, let me also call this initial velocity in the y direction, so that I could put here sine of 30 is equal to the initial velocity in y over 50. And sine of 30 is a half, so this is going to come out to be 25. So I know the initial speed, both x and y. So I'll say it again. You can think of this problem as one speed, 50 at an angle of 30, or you could think of it as this thing has 2 different speeds. One is the horizontal of 43.3, and the other is a vertical speed of 25. And that's how we want to think about it, those 2 separate speeds, because we need to put those 2 separate speeds in separate calculations in order to solve for the motion, because we have to put x's with x's and y's with y's. That's the big step. All right, well, let me keep writing this out. initial velocity in the x plus t plus 1/2 axt squared. So that's kinematic equation number 2. Now maybe I skipped over a little bit of the obvious. Is this a constant acceleration problem?
No.
So we toss something across the room. What's the acceleration? Negative 9.8 in the y direction. Because what is it in the x direction? 0. See, I need to say that twice now. See, last chapter when I asked what's the acceleration, there was only one answer. But now I got to give you 2 answers because there's one for x, one for y. Are both of those constant? During the motion of this, do they stay the same? Does the y always stay negative 9.8? Yes. Does the x always stay 0? Yes. So is this a constant acceleration problem? Yes. So can I use any of these 5 kinematic ones that are only valid for constant acceleration? Yes, and I don't have to use the calculus because we already did it. Yes, good, right? All right, so this is a constant acceleration problem, and that's why I jumped on this, and I probably should have said that, you know, if it's not, I got to do my calculus. Although there's so much hard stuff already in this, we don't give you any non-constant accelerations like we saw in the one-dimensional motion. We're just not going to do that. That's just a step too much right now. Okay. So you are going to see constant ones all the time. So those 5 kinematic equations that are only valid for constant acceleration are going to be valid for this whole chapter. All right, now let me do the same thing for the y motion. So maybe I'll put a y and then a y naught, and then I'll put initial velocity y, then I'll put a t, then I'll put a 1/2 ay, and then I'll put a t squared. So this would be that same second kinematic equation, but notice I've changed everything to y's. And this is really the main thing I want to show you in this first problem, at least this first problem on a projectile, is that I'm going to calculate x's with x's and y's with y's. Okay. So why don't we start putting in what we do know? Do I know the initial position in the x direction? Yeah, right. I actually chose that by saying, let's say the initial position is the origin. So I would say, sure, this is 0. Okay. Do I know the initial velocity in the x direction? I do. Now, that took a little work to get there, but it's not the 50. It is the 43.3. All right, so I'm going to put over here 43.3, and I'll even put in meters per second. Do I know the time? Yeah, they said it hits the target 3 seconds later. All right, so I'm going to put 3 seconds. Okay. Do I know the acceleration in the x direction? Yes, it is 0. Right. So anytime you see a projectile motion, know that in the x direction the acceleration is 0, but in the y direction it is the negative 9.8. And I know it's tempting to put a negative 9.8 here, but that's going to go over here. X's go with x's and y's go with y's. Okay. Now, this alone answers half the question, because it says, where does it hit the target? What are the x and y coordinates? So, grabbing my calculator, I am going to put 43.3 multiplied by 3, and I get about 130 meters. All right, so this target is downrange 130 meters. So that's the x part of it. Well, let's jump over to the y. Okay, so y would be, and let's do the same thinking. This is what I mean by you're going to do one dimension twice. So we got to do the same thinking, but now for the y motion. So do I know the initial position of the y? Yes, I do. I put the origin there. So what's y? 0. The origin means x equals y, x equals 0, and y equals 0. So that's a 0. Do I know the initial velocity in the y direction? Yes, it is 25. Do I know the time? Yes, 3 seconds. Do I know the acceleration? Yes, negative 9.8. Do I know, again, the time? Yes. So I can then just plug this one in too. So I'm going to go 25 times 3. Then I'm going to add 1/2 times a negative 9.8 times a 3 squared. And I come up with 30.9 meters. And so I think that was the only part to it. The x and y from where the projectile lands. I'm going to expand this one step because I was really curious when I was drawing this. Does it hit the target when it's still going up or when it's going down? And I think I can figure that out. Because you see, if it was going down, the y velocity would be negative. If it was going up, the y velocity would be positive. Now, notice the x velocity would always be the same number and always be positive. But just so that I can match, let me just put a line here and say, let me think about kinematics equation number 1. This says velocity in the x direction would equal the initial velocity in the x direction plus acceleration in the x direction multiplied by time. And that same kinematics equation applied to the y would look like this. Velocity in the y direction would equal to the initial velocity in the y direction plus the acceleration in the y direction times time. Okay. So it's kind of boring, but maybe worth doing. What would be the velocity in the x direction when we hit the target? Well, the initial velocity in the x direction was the 43.3 meters per second. And the acceleration in the x direction, help me out again, is 0. And so when we hit the target, the speed in the x direction is still the 43.3. That's the kind of boring one. That's what we meant by no acceleration in the x direction. It starts off with 43.3 and it always has 43.3 on the x direction. It never changes its speed in the x direction. That's what's meant by 0 acceleration. So that one's kind of boring and really doesn't help me answer the question of did it hit it on the way up, so the target was here, or did it hit it on the way down? The thing that's going to answer that is looking at the motion in the y direction. Is it still going up, so the velocity is positive? Or is it on its way down, so the velocity is negative? Did you see a subtlety in there? I asked, is it hitting the target on the way up or the way down? And what I'm looking for is this a positive or a negative? That's the step you have to take. That's a hard step. This would be a really easy question if the question just said, could you calculate the final speed in the y direction? And could you tell me if it's positive or negative? It's a lot harder question when you have to do the physics. The physics being, is it hitting the target on the way up or the way down? Do you see that difference? It's easy when the problem just says calculate the final velocity. Actually, I shouldn't say easy because there's nothing easy about it. I'll say it's easier. Still hard, but easier. But it is really hard when the question says, did we hit the target on the way up or the way down? Because it's you have to say, how do those words translate into math? That's the tough. All right, so the tough part here is deciding, why am I even looking for a positive or a negative? Because if it was positive, it would be going up, and if it's negative, it would be going down. And that's my question. All right, so let's give it a try. So what is the velocity in the y direction to start with? Well, that's the 25. Okay, so here is 25 meters per second. Then the acceleration is negative 9.8 meters per second for 3 seconds. And so I can then say 25 minus 9.8 times 3, meaning it is a negative 4.4 meters per second. And now I've answered what I'm looking for. It's on its way down. I could even probably take this one step further, and even though it's on its way down, it's not very big. It's still a small number. So it's probably more of a picture like this, where it just reached its highest and now it's started to come down. And so it still would be 130 meters as we calculated this way, and 30.9. Well, let me move on to some other ones, but we could even then calculate, what was its maximum height? Actually, maybe I'll go that one. Ooh, I want to show you so much, I guess, yeah.
I was just making sure, so like with what you just did, like the way that we can interpret that information is the target was hit when the projectile was going to the right but downwards.
Mm-hmm. Right. And so it clearly reached some highest point. And so let me not actually calculate, but I would say if the question said what was its highest point, so some point before it got to the target, how would you do that?
Y position.
Okay, so I'm looking for Y position. Mm-hmm. So I would probably use this equation, but don't I need time for that? Because would the time be 3 seconds? No, the 3 seconds is when it hits the target. So I can't directly put it into here because I don't know time. It's going to be something less than 3 seconds. And so what I want to warn you about, you wouldn't use the 3 seconds. Obviously, if you did use the 3 seconds, you would just get this height. So we're expecting to do something less than 3, and we should get something bigger than this. But then how would I get that time? Let me change the question. I'll make it an easier one. Could you tell me the time when it has 0 vertical speed? Well, sure, you would just come over here and put 0 here. Put in your initial speed of 25. Put in your negative 9.8 and calculate the time, right? That's an easy question, right? And I want to emphasize, I'm asking you the same thing, but I'm asking you to figure out that it's at its highest point when its vertical velocity is 0. Same question. One's easier, one's harder.
So if we wanted to find the lowest, we would just use when the Y is 0?
Now the lowest point, I'm not sure I would even mention the lowest point is where it starts on the ground. Yeah. But I'll say it again, what can make the physics problem really hard is when the book or the teacher gives you a test problem that says, find the highest point, and the first step you have to do is that means find where vertical velocity is 0. That's the hard step. Then it's actually pretty easy. You can put a 0 here, you put a 25 here, you put a negative 9.8, and you get the time. You'll get something less than 3, you'll put it into here, and you'll calculate the height. And had they just said, well, why don't you give me the time when the speed is 0? That's easy, because I can just plug in 0. But that's math. That's not physics. And that's kind of my warning here. All right, well, let me keep going here. Let me do number 34 here. And so 34 is a lot like this one. Another projectile. And so it's really going to kind of be the same strategy. And so because of that, I'm going to leave my X and Y columns separately and alone here. I'll set up my board here and get another picture and I'll stand back and read this one. It says, an arrow is shot from a height 1.5 meters from a height 1.5 towards a cliff of height capital H. Okay, just with that sentence alone, I might come over here and say, all right, so I'll do, the arrow is shot at some speed and some angle, and it's going to start 1.5 meters above the ground. And I'm kind of making a decision right here. Where am I going to put my origin? And again, there is no right or wrong answer to this, but by me drawing this point where I launch it, you'll notice that I put the ground at 0. So it's starting at a y value that's non-zero. Now, the x value, I'm putting 0 right where it gets started from. So my initial x is 0, but my initial y is 1.5. And so maybe that's worth writing right here. My initial x is 0, but my initial y is 1.5. And this is the part I was telling you is you could put the origin anywhere you want. You could put it where you launched it, but then you remember you're not putting it on the ground. You're putting it where you launched it. And of course, then this would be a 0. But I think putting it on the ground is going to make the most sense because I think this is going to go on to ask me how high the cliff is, and that's going to be measured from the ground. So it seems like I should put the origin down at the ground this time instead of where you launched it like we did last time.
Why is the initial x still 0?
So I can pick it anywhere I want, but so here's the arrow, and I'm just going to pick the origin right there, right at my feet. So this way, you know, I'm right above the 0. So left and right, I'm at 0. But I'm above it, so y, I'm, right. Okay, so keeping that in mind, that's why I've said in all these problems, you need to think about the math and make a conscious decision where you're going to put your origin. All right, so moving along here, this one says, it is shot with a velocity of 30 meters per second at an angle of 60 degrees above the horizontal. So 30 is its speed. So in this picture, I'm going to put the number 30 meters per second at an angle of 60 degrees. And so it's kind of starting off like this. So it's going to go something like that. Okay? It lands at the top edge of the cliff 4 seconds later. Well, this is a lot like the last problem where it was this target, and sadly I again don't know if the arrow hits it on the way up or the way down, so I will keep that in mind, but maybe I will draw the edge of the cliff like this, and at least at the moment assume it's on the way down, but keep in mind I don't really know that. I'll just kind of draw that in my picture. Okay. So it lands on the top edge 4 seconds later. What is the height of the cliff? Well, I'm hoping you kind of see that this really is the same set of kinematic equations that I just did on the last problem. And of course, we can do both calculations, but let me do the y one first because they actually ask what is the height. Now, as we did in the last one, whoops, my apologies. This initial velocity is x. To do all this, we also have to take that very important first step and write down what is the initial speed in the x direction and what is it in the y direction. So if we call this the initial speed x and this initial speed y, we're saying here, how do you get the components of this speed? So if I do cosine of 60 degrees, I would get the initial speed in the x over 30. And if I do sine of 60, I get initial speed in the y over 30. So this is information that I will need because of that long discussion we had about vectors. We have to think about this not as just one speed, but as two speeds. It's equivalent to being so much in the x plus so much in the y. And I need them separately because I got to calculate things separately. All right, so this is going to be cosine of 60. That's a half times a 30. So that's a 15. Excuse me. 15 meters per second. The other one was that sine 60, which must be 0.866, and then times 30. And so this is 26.0 meters per second. All right, so knowing those, like the last problem, we can come over here and then put this in. So I'm going to put this in, and unlike the last problem, I actually have an initial speed. I mean, an initial position in the y. So this is 1.5 meters is where it starts. It already starts up here. Then the vertical speed is 26.0. In this case, the time is 4 seconds. And I'll ask it again, what's the acceleration in the y direction? Yeah, negative 9.8. So this is a constant acceleration problem. I'm going to use the equation for constant acceleration. I'm going to use number 2 because they're asking for position. And so I get 1.5 plus 26 times 4 minus, I'm just going to put these together, minus 4.9 times 16 and get a 27.1 meters. So that's the height of the arrow after 4 seconds, and since it's hitting the top, I would conclude that the top of the cliff is the same place as the arrow, which is a vertical height of 27.1. So there is the answer to A, what's the height of the cliff? But then we can go on here and say, what is the maximum height reached by the arrow? Ah, that's the same one I was asking you. And I know we're close on time, but hang with me and we'll just start the lab a little later here. But what does that question tell you? How would I figure out its maximum height? Yeah, the vertical velocity would equal 0. So writing down kinematics equation number 1 and asking this question, when does its vertical velocity equal 0? What time does it equal 0? Could be useful here. So the initial speed is 26.0. The acceleration is negative 9.8. So if I take the 26, oops, it's a 36. If I take the 26 and move it to the other side, it's a negative divided by the 9.8. That's also a negative. I get 2.65 seconds. By the way, that helps me answer this question, that it must have reached its highest point at some time 2.65, which is less than 4, so it must have already got to its highest point and is coming down. And it's probably coming down quite a bit, so my picture probably should draw the cliff a little bit further now that I know a little more information. Of course, now let me use this time up here. So I can figure out what is its vertical height at that time. And since it's on its way down when it hits the cliff, the maximum height better be higher than the 27.1. All right, so I will go y equals, and if it's okay with you to maybe save a little time, let me just punch these in instead of writing them down. So this height right here is 1.5 plus the initial speed is 26 multiplied by the time, and that is, I'll just put last answer right there. Okay, then a plus 1/2, then times a negative 9.8, then multiplied by the last answer squared, and I get a 36.0 meters for its maximum height. So you see how I'm kind of reading these as I go along, right? I read the fact that I got a time right here less than 4, which would tell me it reached its peak at something less than 4, so it must be on its way down. And then I used that time to then put it in here and say, well, what would be its vertical height at that particular time? And so it really takes a skill and a lot of practice. So you got a lot of homework problems. That's what they're for, is practice, 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 right? Okay, well, what is the arrow's impact speed as it hits the cliff? Oh, and we got another class coming in, so I'm going to go real quick and say, all right, this would be kinematics equation number 1 to get the speed in the x direction. But help me out here real quick. What's the acceleration in the x direction? 0. So the speed in the x direction would never change, and we already calculated it to be 15. So the horizontal speed is going to be 15. How would we get the vertical speed? Right here, we would put 4 seconds into here. Let me do that real quick. The initial speed in the y direction is 26 minus 9.8 times 4 gives me a negative 13. Let me emphasize that it is a negative. What does that tell me? It's way down, which I already figured that out. Final step, total speed. We got to do the Pythagorean theorem. Did you catch that? And that's why I want to make sure I caught this on the last one. What is the arrow's impact speed? They're not asking for the x component or the y component. They're asking for the total thing. So the total speed squared then would be the 15 squared plus the negative 13.2 squared, and then take the square root. So 13 squared plus, 13.2 squared plus 15 squared, and then the square root, and we are looking at a speed of about 20 meters per second. So it's going down, its total speed is 20. It actually, that speed is made out of 2 pieces. It's made out of 15 in the x direction and negative 13 in the y direction. Those two together is equivalent of 20 coming down at an angle. They don't ask me for the angle, but I think you can do it, and we got to get out of here for the next class anyway. So let's call it a quit. Why don't we start the lab at 11:15, and I think you'll really enjoy today's lab. It's one of my favorite ones because we're going to take a little plastic ball and shoot it across the room, and we're going to do projectile motion and hopefully learn even more about projectile motion and see where the heck it lands. We're going to try to calculate where it lands, and then we're going to see, does it land there? Let's hope it does. All right, more later. Bye now.